I'm Norman Wildberger. In our last few videos in this course in linear algebra, we have been setting up new foundations for special relativity. We've looked at things from a very elementary point of view, in fact, from the point of view of bats, just living in a one-dimensional Newtonian world, and we've seen that without any of the assumptions of Einstein with regard to the homogeneity of the laws of physics with regard to observers or the constancy of the speed of light, without any reference to Maxwell's equations, the basic framework for special relativity is already there from a Newtonian bat point of view. We were looking at different bats or observers moving with constant velocity with regard to each other and comparing how they both measure events in this one-dimensional world in which they live in. And we saw that there were basically a lot of differences, that they ended up disagreeing about lengths and about time and about velocities. And so we might naturally ask, is there something that they do agree with? Well, this is a very important aspect of Einstein's theory, that there is something that they agree with, and it basically comes down to a dot product. But not a Euclidean dot product, rather a relativistic dot product. So that's what we're going to talk about today. We're going to talk about dot products in the context of this one-dimensional space. And then I want to talk about the close connection with an algebraic structure, with the algebraic structure of essentially complex numbers and various variants of complex numbers. So what we're going to do is we're going to introduce complex numbers in a somewhat non-standard way. We're going to introduce complex numbers in the framework of linear algebra, seeing them as sitting inside 2 by 2 matrices. But our point of view is going to be such that we're going to see not just complex numbers, but also two other variants of complex numbers. And we're going to see a triality of structures, of algebraic structures that control rotations in the plane in different geometries. One we're going to call blue, which is going to be the Euclidean one, and the other two are going to be red and green, corresponding to two different views of this relativistic geometry. So we're touching base here with this very exciting development in modern geometry called chromogeometry, but we're also looking at just the algebraic structure from a linear algebra point of view. There's a lot of power in thinking about things from a linear algebra point of view, as I hope you're starting to appreciate. Okay, so roughly what we did in the last few videos, we were talking about two bats, say bat A and bat B. Here are their space-time diagrams, one-dimensional space, one-dimensional time. Here's the timeline of A, here's the timeline of B, and they have two different coordinate systems. A has basis vectors E sub x and E sub t, which are his unit directions in terms of space and time. And bat B has also two unit basis vectors, Ex prime and Et prime. And in the framework that we're looking at things from, which is really the same as A's framework, these two vectors of B are the vectors Rs, this one here, and this one here is Sr. So the reflections of each other in the line y equals x. And we introduced this normalization whereby the actual parallelogram formed by these two vectors here has the same area as the parallelogram formed by A's two basis vectors. That's a normalization that only involves an affine notion of area, and so the two bats can agree on that. And if we do that, then we can assume that these two numbers R and S satisfy S squared minus R squared equals 1. Right, then we had this relation between the two basis vectors of B and the two basis vectors of A, given by this equation involving essentially matrices. So these vectors here have entries which are themselves vectors. And then dual to that is a relationship between the coordinates that A subscribes to a vector and the coordinates that B subscribes to a vector. For example, the vector W can be written as a linear combination of Ex and Et, or as a linear combination of ex prime and et prime. So the coordinates of w with respect to a would be xt, which would be the same as our coordinates for that w, while the coordinates of that w would be x prime t prime according to b. So in this example here, the actual values might be roughly s and r being 5/4 and 3/4. All right, so that might be 5/4 there for s and 3/4 for r. In that case, this w here might be 13/8 and 11/8. That's our point of view on what w would be, and that would agree with a's point of view. A is denoted by square brackets. But b would consider this to be the vector 1.5 because it's one of these vectors and a half of that vector, 1.5 of that one. And note that algebraically, if we take the vector 1.5, that coefficient vector with regard to b, and multiply it by, again, the same matrix S, R, R, S, then we get the coefficient vector for A. All right, so this same matrix is playing a kind of dual role. It's allowing us to write B's basis vectors in terms of A's basis vectors. And it's also allowing us to write A's coefficients of a given vector in terms of B's coefficients of that same vector. And I want to point out some important relation between this vector here and this vector here. Although A and B disagree what the coordinates of this vector W are, they are going to agree on something. What they're going to agree on is that fact that if we look at this combination, this number squared minus this number squared, okay, 13/8 squared minus 11/8 squared, well, that turns out to be, if you calculate it, 3/4. And that's exactly the same as 1 squared minus a half squared. So there's a quadratic form here, this quadratic expression of the x coordinate squared minus the t coordinate squared is going to be the same for A and B, even though the x and t coordinates themselves are different. All right, this is sometimes called the interval in relativistic geometry. That's not a word that's used in the mathematical side of things generally. And we're going to see that this is really just an example of a quadrant. So I'm going to introduce this terminology that we're going to call this the Einstein quadrants. Okay? So this number here, this quadratic form applied to a vector, either this one here or this one here, we're going to call that the Einstein quadrants of the vector W. And the point is that this is something that the two observers can agree on. And so it becomes a foundational aspect to the theory if we can frame our physics in terms of quantities that have this kind of nature, that they can be viewed the same way by different observers. Hey, then we get a physical theory which has, broader extent than otherwise. Okay, so now we come to a very exciting development. We are going to introduce this relativistic dot product that's implicit in that previous slide. But we're going to do so in a somewhat interesting way. We're going to view it as one of three interconnected, equally interesting dot products. There's actually a triality or a threefold symmetry in planar geometry that historically has gone almost unnoticed. And it's only really been in the last 10 years that this triality has been discovered and developed, and it's really one of the most exciting developments, I think, in planar geometry. So it's called chromogeometry, and we're going to introduce it here in the context of linear algebra, in the context of three dot products all existing in the same context. All right, we're going to call them blue, red, and green dot products, and one of them is very familiar. The blue one, this one here, is our usual standard Euclidean dot product that we've already spent quite a lot of time discussing in our earlier videos. All right, so here's a vector x1, y1, here's a vector x2, y2. They're row vectors now. Okay, maybe convenient to work with row vectors. And we're going to introduce this dot product, and there's going to be a little b underneath it to denote the blue dot product. And that's x1, x2 plus y1, y2. And now you won't be surprised to see this new dot product, this relativistic dot product, that we've already seen in the context of our oriented circles. And this is intimately connected with the special theory of relativity that we've been talking about. So here the dot product between the same two vectors is x1, x2 minus y1, y2. And then there's a green one, a third one, which may seem a little bit different, but it turns out to be intimately connected with the other two. And in some sense, it's a kind of a null line version of the relativistic dot product. It's what you get when you look at the relativistic dot product from the point of view of those sound directions, the 1, 1 and the minus 1, 1 sound directions. Okay, so here's the green dot product. The dot product is x1, y2 plus y1, x2. Now these are all symmetric bilinear forms. Please check that. Please check that we have the bilinear condition for all three, and then we have the symmetric condition for all three. And associated to these three bilinear forms or dot products, we have three notions of quadrants. So the quadrants of a vector, I remind you, is just the vector dotted with itself. So there's three ways of dotting a vector, so there will be now three different quadrants that we can look at the same time. So the blue quadrants is the usual familiar Euclidean one. It takes a vector xy, and its value is x squared plus y squared, the dot product of xy with xy. The red quadrants will be x squared minus y squared. And the green quadrants, if you plug in here xy and xy, you will get xy plus yx for a total of 2xy. So this is the green quadrants of the vector xy. Okay, so the study of these three different geometries essentially at the same time is quite a novel way of thinking, I think, because it goes beyond this well-established paradigm that was initiated by Felix Klein in the 19th century called the Erlangen program. Well, Klein said, geometry is essentially the study of a group of symmetries of some situation. And what we're doing here is saying, well, that's fine, but we want to go beyond that. We want to be looking at an object with more than one group of symmetries, with more than one geometrical structure imposed on it. So we're looking at the plane, and now we're looking at it simultaneously with a blue dot product and corresponding Euclidean geometry, and with the red and green dot products, which give us corresponding relativistic geometries. And the claim is that these three geometries are somehow very closely connected. If something is true for one of them, it's probably true in some way or another for the other two as well. Not always, but often. And moreover, that the three geometries together have this intimate interconnection. Okay. So this is initiated in my paper Chromogeometry, which appeared in the Mathematical Intelligencer, Volume 32, Issue 1, 2632. I notice I didn't put a date here. Probably the date is something like 5 years ago. Okay, an initial theorem is that if we look at these three quadrants, that there's a reasonably obvious algebraic relationship between them, which goes back to Euclid. Okay. We just observe that the blue quadrants squared equals the sum of the red quadrants squared plus the green quadrant squared. Basic, elementary, Pythagorean, triple kind of identity. Right, so I hope that's completely obvious to you. But it shows that already at this level of just quadrants that there's some connection between these three geometries. Okay, it's an important relation, even though it's very elementary. One way of thinking about a dot product is in terms of a linear algebra framework with matrices and a symmetric matrix which captures the dot product. So for example, the blue dot product can be written in matrix language by taking the vector v, which is a row vector, and taking the matrix 1, 0, 0, 1, which is just the 2 by 2 identity matrix, and multiplying it by the transpose of W. So transpose of the vector is, instead of having the row vector xy, we have the column vector xy. All right, so if you take this 1 by 2 vector v, you multiply by the 2 by 2 matrix I, and then by the 2 by 1 matrix W transpose. The end result is a 1 by 1 matrix, or what we can think of as simply a number. And that number is the dot product between V and W. Please check that yourself by doing the matrix multiplication. Make sure that you appreciate that the dot product can be written in this matrix form. Once we have it that way, well, then we can say, well, what about the red dot product? The relativistic one with a minus sign. Well, it's given by a very similar expression. It's just that the identity matrix here is replaced by this matrix, 1, 0, 0, minus 1. This minus 1 here will generate that negative sign in the dot product. The green dot product is a little bit different, but it's also given by the similar kind of formula. But now this matrix here is the matrix 0, 1, 1, 0. So please check, okay, that each of these claims is true, that the green dot product really is given by this matrix multiplication. And let's note something about these three matrices. They're all symmetric matrices. Right? If you reflect them about the diagonal, you get the same matrix. In other words, this entry and this entry are the same in all three cases. So these are all symmetric matrices. There is a fourth matrix around that kind of complements these three to form a basis, a natural basis, for the linear space of 2 by 2 matrices. I remind you that the space of 2 by 2 matrices is a four-dimensional linear space or vector space. And here is a basis for that four-dimensional space. In other words, every matrix, which is 2 by 2 matrix, can be written as a linear combination of these four matrices in exactly one way. And these are the three matrices that are appearing here with the blue, red, and green geometries. And this other matrix is not a symmetric matrix, it's a skew-symmetric matrix, which also plays an important role in geometry. What does it mean? Why? It's because this matrix basically captures the affine notion of parallelism of two vectors. So recall that two vectors x1, y1 and x2, y2 are parallel. That means that x1, y2 minus y1, x2 equals 0. That one is a multiple of the other. Like 2, 3 is parallel to 4, 6. 4, 6 is a multiple of 2, 3. So it's the same kind of relation that we have when we have fractions, that a over b equals c over d, when ad minus bc equals 0. It's exactly the same story. Now this relation can also be written in this kind of matrix form. We can write it as x1, y1 times this matrix, 0, 1, minus 1, 0, times x2, y2. Let me just check that for you, right? If we multiply this vector times this matrix, what we get is the vector minus y1, x1. The combination here is replaced with minus y1, x1. And then when we multiply by this vector, we get minus y1, x2 plus x1, y2. Exactly that expression there. So this is very interesting and shows, I think, already very clearly that these three geometries are somehow, sitting naturally inside the world of 2 by 2 matrices. We have this matrix representing parallelism of two vectors. It's a skew-symmetric matrix. And these three vectors, natural basis for the symmetric matrices. And from our point of view, they correspond to blue, red, and green geometries. Each one defines a bilinear form. Each one defines a geometry. And these three geometries interact. All right, we've seen earlier that if we have a dot product or a symmetric bilinear form, then there's various things that we can do. We can introduce the notion of quadrants, as we've done. We can also introduce the notion of perpendicularity. We can talk about projections. We can talk about circles and various things like that. So what we can do really is the same kind of thing with these three planar geometries. In the Euclidean case, we've basically done this all before. It's very familiar. But what I want to do now is I want to show you these corresponding concepts together in the context of all three geometries at once, so we can see them together. All right, so the notion of perpendicularity. We know very well what that means, that when we have a dot product, that we define two vectors to be perpendicular when their dot product is 0. Well, we have three dot products that we're considering here, the blue, red, and green. So we have three notions of perpendicularity. Three notions of perpendicularity. V is blue perpendicular to W, precisely when V blue dot W is 0. V is red perpendicular to W, precisely when V red dot W is 0. And V is green perpendicular to W, precisely when V green dot W equals 0. To try to give you some idea of what that means, here's a useful additional definition that we can make. Suppose we have a vector v, which is xy. Right? Let's define three other vectors, which we might call sort of rotates of the vector v. So the blue rotate, v super b, will be defined to be minus yx. Right? So v is xy, then v super b is minus yx. v super r is yx, and v super g is x minus y. So then it's almost immediate that the original vector v is blue perpendicular with v super b, it's red perpendicular with v super r, and it's green perpendicular with v super g. For example, the Euclidean dot product is this times this plus this times this, that's obviously 0. The red dot product here is xy minus yx. That's obviously 0. And the green dot product between this and this is x times minus y plus y times x, which is also 0. This allows us to see what perpendicularity means, and it's very important that we understand this, that we have a visual understanding of what perpendicularity means. So if we have our coordinate axes, x and y now, and we have an arbitrary vector v. Let me just put this vector here, right? So let's say that happens to be the vector v. Or maybe I'll put it here. Okay, that's the vector v. So it's the vector xy. Where would v sub b be? V sub b would be this vector here. Okay, if that's the vector xy, this is the vector minus yx, which is traditionally, as you can see, perpendicular in the usual Euclidean sense to the original vector. What about this vector v sub r? Where is it? It's obtained by interchanging the coordinates. So if this is the vector v, then the vector v sub r will be this one about here, which will be the reflection of this one in the line y equals x. Right? That's the vector v, and that will be the vector v sub r. Now what about v sub g? There we're keeping the x-coordinate the same and negating the y-coordinate. So if this is the vector v, then if we negate the y-coordinate, then we get this vector here. So it's just the reflection of this vector in the x-axis. So here's how you can think about perpendicularity in the three different contexts. That blue perpendicularity is the usual one that we already know, the Euclidean perpendicularity. The red perpendicularity amounts to having two vectors which are reflected in the line y equals x or in the line y equals minus x. while the green perpendicularity amounts to reflecting a vector in the x-axis, or as it turns out in the y-axis. So if you take this vector and you reflect it in the y-axis, you also get something which is green perpendicular to what you started. Okay, so here's an exercise for you. Show that these three vectors also have another kind of relation, which is another sort of early manifestation of this chromogeometry business. That V super R and V super G are blue perpendicular. And that correspondingly V super B and V super G are red perpendicular, and that V super B and V super R are green perpendicular. Alright, so now I want to show you an interesting aspect of this story. So here is a point A, and here is a line L. And we know that in ordinary geometry, a standard construction going back to Euclid is to drop a perpendicular from A, the point A, to the line L. In the usual Euclidean story, this perpendicular, or sometimes called altitude, would be this line here. This blue line is blue perpendicular to L. I've also shown you the red altitude and the green altitude from A to the line L. So notice that this line here really is red perpendicular to this one here. All right, if you look at that intermediate line, that's a slope 1 line. And notice that this green line really is perpendicular in the green sense to the line L, because they're reflections of each other in the coordinate axes, either in that axis or in this axis. But there's something else that's kind of interesting in this diagram. Once you have these three altitudes from A to the line L, then you may notice something else. You may notice that these two altitudes are red perpendicular. The green altitude and the blue altitude are red perpendicular. And that the blue altitude and the red altitude are green perpendicular. Can you see that? And that the red and the green altitudes are blue perpendicular. So this is typical of chromogeometry. These three different notions of perpendicularity, these three dot products, are interacting with each other. We want to consider all three of them at the same time. It's very important. It's not just blue and red, Euclidean and relativistic. You want to consider the Euclidean dot product along with both relativistic dot products, the red one and the green one. We know that once we have a dot product, another interesting thing to ask is, what are the circles looking like? And for simplicity, we'll look at unit circles, circles which are centered at the origin and whose quadrances are units. What's a unit? Well, 1 is a unit. And -1 is also a kind of unit. If we look at the blue situation first, that's very familiar. We talked a lot about circles, Euclidean circles. There's the unit circle in blue, centered at the origin, going through the point 1, -1, 1, -1 in the x and y directions. If we ask for a circle where the quadrants is equal to -1, x squared plus y squared equals -1, over the rational numbers, there is no such circle, and so we hardly ever consider it. Although you probably know by now that that is actually also an interesting circle. Here is a red analog. So if we look at the red quadrants and ask when is that equal to either 1 or -1, then we're talking about equations x squared minus y squared equals 1 or -1. And those are hyperbolas. Here's x squared minus y squared equals 1, and here is x squared minus y squared equals -1. Notice that they're touching the blue unit circle. In terms of the green unit circle, well, the quadrants is 2xy, so we are interested in 2xy equals 1 or 2xy equals -1. Those are green circles. And they're familiar from calculus. It's like the equation y equals 1 over 2x. those are hyperbolas also that look like this and this. That would be 2xy equals 1. And 2xy equals minus 1 would be these ones here. Notice that they're also sort of tangential to the unit blue circle, but the point of contact is actually not existent over the rational numbers. Right? There is no 1 over root 2, 1 over root 2 number. So there's no actual point that lies on those two, but nevertheless they're sort of geometrically tangential. All right, so when we have a geometry, a natural thing to do is to look at isometries, transformations of the plane which preserve the dot product. So we're looking for matrices, say A, which satisfy V dot W equals VA dot WA. We're talking about row vectors here, so the matrix A will multiply a row vector on the right to give us another row vector. So if we have such a matrix A for which this relation is satisfied for all V and W, then we can call A an isometry. All right, now if our dot product is given itself in terms of multiplying by a symmetric matrix M, so V, M, W transpose, as are our three blue, red, and green dot products, then this condition can be written in this pleasant way. So V, M, W transpose, that's that thing there, and then this condition here will be VA, the dot is multiplying by M, and WA transpose is A transpose W transpose. When you take the transpose of a product, you get the product of the transposes. And if we look at these two equations and compare them and ask, well, when is this going to be true for all V and W? Then we get the condition that this matrix M here and this inner matrix A, M, A transpose ought to be the same. So this is the condition that's required on an isometry, that M equals A, M, A transpose. So if M is the symmetric matrix that encodes whatever bilinear form we're looking at, be it blue, red, green, or otherwise, this is the condition for a matrix A to be an isometry of that geometry. So it's a very important condition. Notice that there's a transpose here. So it's A times M times A transpose equals M. If we can find a matrix A or matrices A that satisfy that condition, then they will be isometries of our geometry. All right, so I want to show you the isometries. So I want to show you now the basic isometries that go with each of the three geometries. But I want to do it sort of all at the same time so you can see all three of them in front of you at the same time. We could also have done each one separately, but I think it's useful to see them all together to be conscious of the interconnectivity between these three geometries. So here are the three matrices that encode the three dot products, the blue, the red, and the green. And here are the conditions that we required, that we derived just previously, on a matrix A, that A times M times A transpose should equal M. Okay, and we're observing that in the blue situation, this matrix here, SR minus RS, satisfies the condition. Here's the matrix, here's its transpose. If S and R satisfy S squared plus R squared equals 1, then if you perform this matrix operation, multiply those three matrices together, then please check that the resulting matrix is 1, 0, 0, 1. In other words, this really is an isometry in the blue geometry. In fact, it represents a rotation. It represents a rotation that sends the vector 1, 0 to SR and sends the vector 0, 1 to minus RS. So we're actually acting on rows here in this setup. So this is really a description of rotations in ordinary Euclidean or blue geometry. All right, now to go to the red geometry, it's a kind of a variant of this. The matrix representing the dot product changes. This 1 becomes a -1. And so we correspondingly have to fiddle around with the matrices. We have to adjust them a little bit, but not much. This minus sign that appeared here disappears. And here the minus sign also disappears. And then you can check that this times this times this will equal this, provided this condition is satisfied between S and R, that S squared minus R squared equals 1. And I hope this is familiar. I hope you can remember that this is the matrix that we've been talking about, plays a central role in our development of special relativity. This SRRS matrix satisfying the condition S squared minus R squared equals 1. This formula shows us that these matrices are exactly isometries of this red geometry. This is the algebraic manifestation of Einstein's observation that the Einstein quadrants is unchanged under these Lorentz transformations. And what about the green story? Because we want to do all three at once. Well, here's the matrix, the symmetric matrix that encodes the green dot product. And here we find matrices and their transposes. When we multiply this times this, we get this, provided that this condition is satisfied, that SR equals 1. So, in the green geometry, we also have isometries, which you can think of as rotations, but they are perhaps somewhat simpler. Many things are sort of simpler in the green geometry, even though sort of geometrically the green and the red turn out to be pretty close to being the same. Nevertheless, algebraically, the green geometry is often simpler, which is why physicists like to use this kind of framework. They call this sort of the null basis approach to special relativity, where you change your coordinates so that the null vectors are the basis. So please check this condition here. And here I'm just repeating that fact that in the red geometry, the change of basis matrices SRRS that we've talked about, where S squared minus R squared equals 1, we now see that they are actually isometries of the red geometry.